And well, don't you feel like there could have been more? Yeah, like I was expecting, more crunch in the middle. Oh, yeah.
How do I plug it in? Because I haven't been able to figure out where
Oh, no.
it'll let me plug it in.
I'd have to maybe like look with you on that.
Okay.
Because I thought there was just like where you
Yeah, 'cause I
register.
have it pulled up here, and it doesn't show like a spot to plug it in, or maybe I'm just missing it. It's also entirely possible.
If you do continue shopping, because you need to put in,
Because I already have, it let me sign up for the lab and the recitation, just not the lecture.
so annoying. If we go, so we go down to instructor permission. Then if you add
Sweet.
the code, that might work that way.
Thank you.
All right, any questions before we get started? So don't forget to register. And I know some people emailed me, so do that. I think I'll also try to go through the roster, and then I already made a column in Blackboard saying like extra credit. So I'll kind of do that, just make sure that I update it appropriately. And then just like last year, you know, let's say you don't register or you're not taking this class, although I hope all of you do. Just, you know, send me an email. I have other plans or I'm taking other classes, blah, blah, blah. But I highly encourage everyone to finish this series of chemistry. I know not all majors require all 3 terms, but sometimes you get like screwed later on down the line when someone says, well, how come you didn't take all 3 quarters? And like, well, my major didn't require it at the time. And then later on, you know, someone else wants you to have the full series. So I encourage you to go on and complete it if you can. If you have room, I would do it. And so just register ASAP. And again, so they can open up another lab section, because right now there's only 1 lab section. But I'm hoping that everyone will continue and make it, and then we'll need 2.
Do you know the times for the lecture?
I think it's going to be the same time. That's
It is right now?
yeah,
Okay.
yeah. I took a poll last week in class, and everyone kind of liked that time, so I submitted it. That yes, let that be the time. I'll
Okay.
double check on the schedule. Although if you're telling me you don't know the time, maybe it hasn't gone through. So
I mean, it's when I registered like last
okay,
week, so
yeah.
it will be updated.
I'll take a look at that and see. But yeah, it should be updated, should be the same time. I think everybody kind of liked the schedule a little better compared to fall. And then just make sure to get on top of your assignments. So it is week 8. That's kind of scary. So I'm slowly catching up on grading the labs. But as I'm grading the labs, I noticed many of you are missing labs from me and owe me tons of labs from the first week. So get those in ASAP. You know, bug me for help if you're just like missing some things. It's whatever you need to get you over that line. Because I want people to start turning in stuff. Don't wait till week 10 to the panic. Although I know that's what happens, but try to get it in sooner rather than later. Again, happy to meet and help you guys in any way. Other questions, comments, concerns? So now this brings us to chapter 18. And so ask questions. Chapter 18, I feel like is a little, it's basically we're building off of chapter 17. It's like, okay, we learned how to determine our reaction orders from our experimental data, and now we're kind of taking it the next step further. is how do we determine the reaction mechanism, and of course that reaction mechanism has to be consistent with whatever we found experimentally. Again, based off of 17. So if you need me to slow down, just let me know, ask questions, because again, it's kind of building upon 17 here. And so now let's look at reaction mechanisms. And so, in general, we just kind of simply describe our reactions as a reactant and product. However, that doesn't really describe, what's actually going on in the molecular level over who's, kind of exchanging and all that quick steps. I think your textbook even mentioned that such a simple reaction like H2 plus O2 to give you water, right? Super simple, or at least deceptively simple. And we don't even know the reaction mechanism for this reaction. And so I think your book said that maybe it could be even 10 steps, don't know. And so this all depends on like how fast the reaction occurs, what are the intermediates, and that kind of determines like whether you can even determine the reaction mechanism. So this is really difficult to do just as a scientist. You can get the reaction, you can see product reactant, but then trying to really understand the mechanism is very difficult, and it can't always be found. So that's just limitations of your spectroscopic machines, and then obviously the reaction conditions. And so the other thing is, and so in these kind of reactions, we're just thinking, well, the probability of more than 3 molecules colliding at the same instant with proper orientation and sufficient energy to overcome a barrier is negligible. So that just means, especially if you see, an overall reaction where you have 3 molecules combining, that's probably not the mechanism, because you're not going to have 3 molecules smashing together to make your product. There's some sort of steps in between. And so that means that most reactions occur in a series of small reactions involving 1, 2, or at most 3 molecules. And so again, that's breaking down kind of our overall reaction and then breaking it down into further parts and trying to understand what's going on. And then so we want to describe the series of reactions that occur to produce the overall observed reaction, and of course that's our reaction mechanism. And so again, the rate law, whatever we find with this reaction mechanism, we break it down. It still has to be consistent with whatever we found with our reaction orders, right? Just like we saw in chapter 17. So let's kind of look at that. And so if we look at this overall reaction, we're just looking overall. So H2 plus iodine chloride gives us 2 equivalents of hydrochloric acid and iodine. And so again, this is just what we observe, right? Reactants gives us products. And now the mechanism attempts to break it down into actually, well, what is going on in our little flask, in our chamber, at a step-by-step level. And so the reactions in this mechanism are the elementary steps, meaning we can't break them down into further simpler steps, and that the molecule actually interacts directly in this manner without any other steps. So that's just saying, right, this is what's going on. So we have this overall reaction, but now we can see it's kind of broken down into 2 steps here. And so looking at this, do you notice something that's maybe in our mechanism, but not a reactant and not a product? So what do you see in there? Anything jump out? Yes, exactly that. HI over here. So good. So you want to get used to kind of picking that out. So we notice HI, right? It's not a reactant, not a product. And so instead this is called an intermediate. So this is just some sort of species that's fleeting. Obviously, we care about it in the reaction mechanism. It's part of our intermediate product, right? But then that HI continues to react with another equivalent of iodine chloride to make HCl and iodine. So that's good. So that's one thing you want to be able to do, identify your intermediates. again, I'll highlight HI again. So that's our intermediate. So again, something that is not a reactant or a product, and it is consumed then in our second step. So again, those are intermediates, so anything that is produced in an early mechanism but then is later consumed. And so again, when we look at these intermediate steps, we can also talk about, so the number of reactant particles in each elementary step is called its molecularity. So if you have some sort of unimolecular step, like maybe radioactive decay is a good example of unimolecular. You have one particle splitting. Bimolecular involves two particles. They could be the same particle. So it just depends, right? So bimolecular means you have to have two particles colliding, and again at the proper orientation. So that's probably what's going on here, right? So the first step, H2 and ICl have to collide. Then that makes this product. Then our hydrogen iodide, right, continues on to react with another equivalent, again, in that probably bimolecular step, just two things meeting to create our next step of products. And then, so like we mentioned, this termolecular step, this would involve three particles, but this would be very rare for one of these intermediates. And again, you can imagine just probability, right, wise, you have everything, you know, floating around, colliding, like we've talked about before. So trying to get three particles to collide at the proper orientation is pretty rare. So probably wouldn't see that, but, you know, it could happen. And so this also means that we can break down each little step into its own little reaction, because that's, again, what's going to be happening. And so they have their own activation and own rate law for each individual step. And so again, we had said, and we can't say this enough, so the rate law for our overall reaction must be determined experimentally. So we saw that last chapter going through the data, like, and you did that with the iodine clock. But then the rate law of each elementary step can be deduced from the equation of the step, and then of course you would check it at the end. Does it match what we determined experimentally? So then the first thing you want to be able to do as well is just be able to write out, you know, what these are using variables, and then again, of course, you can compare them to your final rate law. And so all this is saying we don't have any information here, and we're just calling this, right, K1 because it's our first step. So we just have our rate is equal to K1, doesn't really matter what that is, times our amount of hydrogen plus our amount of iodo-chloroform here. And then K2, so again, K2 just means step 2, so that means the rate of that reaction is just K2 times our concentration of HI times our concentration of iodo-chloroform. And so that's just writing it out, right? We're not comparing anything yet to the overall data. This is just kind of breaking it down into those steps. So this is more like mathematical formality anyways. And then so comparing this then for our elementary steps, so if we just had, again, one product of A, then whatever step, the rate would be dependent on, of course, our K, again, just a variable times A. If it's two equivalents of A coming together in a bimolecular step, so notice molecularity is 2, so 2 A molecules colliding, so then we get K times A, then squared if you need two of them. If it's two, like A and B, that have to collide together, then your rate is equal to K times A times B. And then, of course, you could have all these permutations of the three products, which, again, are all rare. So if you have to have three equivalents of A colliding together, that's A cubed. Or if you have AAB, A squared times B, and, of course, ABC, three things coming together. And, of course, your rate is ABC. Questions so far? Trying to go slow. And so now let's tie this back to our previous chapter. So our rate determining step then is going to be the slow step of our reaction mechanism. And so most mechanisms, there's one step that's kind of called the rate determining step that occurs slower than other steps in the mechanism. And again, this will probably be reflected back into the overall rate law that we observe. And so the result is that the product production cannot occur any faster than the slowest step. So that makes sense, but kind of key when you're getting into the math. And so that step then determines the rate of the overall reaction. And so usually it's because that slowest step has the largest activation energy. So if you kind of remember, right, we have our activation energy. That's why we like catalysts or other alternative pathways that make that slow step go faster by providing an alternate route. And so again, I'll just start that. All right, so let's continue. So now we're looking at this reaction. So we have nitrogen dioxide plus carbon monoxide gives us nitrogen monoxide and carbon dioxide. And so we can see, so this would be based off of some data that our rate observed for our overall reaction is K times the concentration of NO2 squared. So then, right, we can also tell ourselves, well, that means it's zero order for CO, again, just as a reminder. And so now we can break this down into kind of the proposed steps. And so if we look at these two steps, so we have that two molecules of NO2 have to collide together, and that makes nitrogen trioxide plus nitrogen monoxide. And so, of course, the rate of this first step is equal to K1, again, just 1 because it's the first step, times NO squared. So we have NO plus NO colliding. And then if we look at the next step, and let's say they hadn't told us who was slow, who was fast, so then we look at their next step. So our next step is, again, just generic K2 times our products, or excuse me, reactants, so nitrogen trioxide plus CO. And so if we kind of compare our rates here, so if we knew this information and then we were comparing our two potential rates, well, right away we can see, well, this happens to match our observed rate law. So this probably means then that this is the slow step, this is going to be the rate determining step. So this reaction, right, we could solve it and substitute NO3 for NO2. We'll look at that later. But we would still have the factor of CO, right? Except it was zero order for CO. So this step has to occur so fast, right, that it doesn't matter. Because that's what we had established, right, for zero order. So changing the concentration of CO has no effect. So therefore, right, this rate doesn't matter. So it must be the fast step. And step 1 has to be our limiting slow step. Yeah.
I don't know how to formulate this question. So you would know that the first step of that proposed mechanism would be two NO2 molecules just by the rate order? So like, how did you know that NO2 plus CO was actually going to begin with two NO2 molecules? Like, how would they know that?
Like,
Right
how do
there.
they know this?
Yeah.
So this could be trickier to determine. So this is where you would probably have to do like labeling experiments and all sorts of like manipulation, and then you see like, you know, can we change the rate? How does it affect the other step? And then you kind of like propose. So usually how these things work is like, you know, you kind of propose, let's say you propose this, right? Okay, I think this is the mechanism. But then you would have to do like different experiments, maybe manipulate, see if you could do just this step, NO3 plus CO, isolate that, how fast does that go? And that's why these reactions are like really tricky to determine like in real life. So I don't know if that answered your question, but.
I think I want to, I think the answer that I'm looking for is if we would be required or expected to know that that mechanism would begin with the NO2 because the observed rate is K and then NO2 squared.
It's a pretty good indicator, but that being said, like maybe there was something else that happened, but yeah, this is probably like a good indicator that yes, you would need two equivalents happening because it's some squared, but yeah. But yeah, you never want to make too many assumptions with these proposed mechanisms, so that would give you like a good starting point, but then that's where you have to do all the experiments and labeling experiments and
So it's like not always like that.
yeah.
Okay.
And so again, just emphasizing, so of course our first step is slower than the second step because it must have a larger activation energy. And so again, the first step in this mechanism is the rate determining step, and it is the slowest step. And so the rate law of the first step is the same as the rate law of the overall reaction. And so this kind of gets into maybe what you were asking. And so validating a mechanism, again, it's not trivial at all. Like, you can do experiments and experiments trying to figure out mechanisms. That's why people publish papers and argue about this like all day, because it's, again, difficult. And so to at least validate, and even then, maybe you won't fully prove a mechanism, there's two conditions that must be met. So again, the elementary steps must sum to the overall balanced chemical reaction. And so that's fairly straightforward. So if we go back and look at this mechanism, well, I can see, this intermediate cancels out. And that leaves us, let's see, and this intermediate cancels out. And so that gives us this overall reaction. So just summing up all our reactants and all our products. So we have NO2 plus CO gives us NO plus CO2. Okay, that checked out. So you want to double check that. And then again, the rate law predicted by the rate determining step must be consistent with the experimentally observed rate law. I think that's straightforward, at least for now. And so you might see a mechanism that contains a fast initial step, and then of course your rate limiting step may contain intermediates, and then of course you could back calculate it to your initial reactants to maybe match up with your whatever reaction order was determined. So when a previous step is rapid and reaches equilibrium, the forward and reverse reaction rates are equal. So that's good to note when you're doing math. And so the concentration of reactants and products of the step are related, and the product is an intermediate. And then we'll see how to substitute them into the rate law of the rate determining step to produce a rate law in terms of just reactants. All right, so let's look at that and see what we mean. So we're looking at this reaction. And so they gave us the overall reaction. So let's start with that. So we have two equivalents of hydrogen plus two equivalents of NO gives us two equivalents of water and one equivalent of nitrogen. And so they told us that the rate observed for this reaction is sum K times H2 times NO squared. And then we're given these steps. So we have, they told us that the first step is fast, this is proposed. And then we have a slow rate, and then another fast rate here. And of course, what's the problem with this slow rate? So it has intermediaries, so we can't relate it to this rate observed, at least not yet. But what we can do, so let's start by just writing out what we have here. And so we have our forward reaction, K1, which would give us NO squared. And then they made the point, so the forward and reverse reaction rates are equal. So that means we could say, so K1 is going in the forward direction. So if you take the inverse, so that would be K negative 1 is then equal to our N2O2. So that's our first key point, right? So this is the rate of which it's dependent upon, and that equals to the rate that our product is being formed at. So that's a good step. Then we can also substitute in, just in case if we need it. Well, I don't think we need it, because we could write out our other fast step, but it's probably irrelevant. But we have H2 times N2O2, or N2O. So again, probably don't need that. So what we want to do, though, is get our slow rate in terms of our reactants. So we can do some math over here. And so we're given kind of this substitution. And so we can see, right, our rate of N2O2 is going to be equal to our forward direction of NO squared over our backwards direction of K1. So you could just substitute that. So that's just manipulating this over here. So manipulate, so this gives us N2O2 is equal to K1 times, NO squared over K negative 1. So we get that. And then from there, we can substitute in. So if our slow rate is given by this equation, so let's just rewrite that. So we said our slow rate was K2 times H2 times NO squared. Oh, sorry. That's not what we said. Looking at too many things. Sorry. Times N2O2. And so now we can substitute in for N2O2 this expression. So substitute for N2O2 since we don't want those intermediates. And so now that gives us our slow rate. So K2 times H2 still times K1 over K negative 1 times NO squared. So just plugging that in, right? And then all these K's can kind of cancel out because they don't really matter. This just gives us our overall kind of new K that we have to find or determine. So this gives us K times H2 times NO squared. And then the next question is this the reaction mechanism we observed? Yes. And so this looks good and is consistent, again, with our observation. Oh. Give everyone a second to take that in. Sorry, were you done looking? So let's try another one. And I think I meant to give you extra data for this or something. So I think there was supposed to be a part that says the rate is equal to K times ozone squared times oxygen to the -1. And so first thing we can do, we want to write out our overall reaction for this. And so all that is adding up our reactants and products. So I cross out any intermediates. So we have these oxygen radical intermediates. So this gives us some equation. Looks like 2 equivalents of ozone react to give us 3 equivalents of O2. And so then we can substitute and compare. And so once again, so I'm going to rewrite this for a second. So we have ozone. So K1 forward direction, K -1 backwards gives us O2 plus oxygen radical. So we said that was fast. But then we can still write the expression. So then our rate is determined by K1 times ozone. Then if we repeat that, so our slow step they said is ozone plus oxygen radical to give us 2 equivalents of O2. So again, we can write that as K2 then times ozone times oxygen. Then if we substitute again, so then we can also write, so K1 is also equal to, so looking at this fast step going in the backwards direction, because again we said they were equal at equilibrium, then that would be equal to the rate of K to the -1 times O2 times oxygen radical concentration. And then if we wanted to rewrite K2 then in terms of our other species, so let's substitute for our oxygen radical once again. So I'm going to do oxygen is equal to K1 times O3 divided by K -1 O2. So then we can sub back in. So plug that into there. And then that gives us K2 times O3 times K1 times O3 divided by K -1 O2. So then we can rewrite that as our overall, again, new generic K. Now we have 2 ozones. So ozone squared divided by our oxygen concentration. And so again, that's what was given to us in the beginning, and then we got it back out in the end there. So that matches. Any questions about that one? I'll give everyone just another minute or two to copy that over. So far it's mainly just a lot of variable substituting. And again, just seeing our forward and backwards reaction rate on our fast steps as kind of helping us get to our slow step. And so the other thing that we can do is, of course, determine the effect of temperature on rate. And this is also what you did with your iodine clock. So that's why you did it at a cold temperature, to see how does that change it. And so we have this Arrhenius equation. So our relationship for K is equal to A, which is just our constant, times e to the power of negative activation energy over RT. And so let's look at all these units. So temperature is always in Kelvin, so I think that's pretty standard for chemistry we're seeing. So Kelvin, Kelvin, Kelvin. R is this different gas constant. So if we care about energy, we want to use this 8.314. So that's joules per Kelvin mole. Our EA is our activation energy. So whatever we need to get over that hill, so that's always good to be able to calculate so we can be able to compare reactions. How big is the activation energy? And then A is just our constant. And so the rate the reactant energy approaches the activation energy. And so you'd have to determine this. And so again, we've seen this diagram before, just our very generic. We have two reactants and then make products, so some sort of intermediates or activation energy. We also mentioned, right, our transition state occurs there. And then this gives us product. Of course, this is just assuming a simple step here. And so again, there's an energy barrier to all reactions. The activation energy is the amount of energy needed to convert our reactants into the activated complex. And so that activated complex is known as the transition state. And the activated complex is a chemical species with partially broken and partially formed bonds. So of course, it's also very high energy. And it could look something kind of most common, maybe not most common, but you can have something like this. So if you're doing some sort of substitution reaction, maybe carbon is breaking this CX bond as it's forming a new CY bond. And so you have some sort of high energy transition state where carbon at that point kind of looks like it has 5 bonds. So obviously that would never be a stable state. This is just some sort of high energy transition period. And then it really depends, again, on the reactant and obviously the transition state on whether you can observe this or not. So spectroscopic techniques, they are incredibly powerful. Like I mentioned, right, you can watch your reaction kind of go in a J-Young tube. And so maybe if you're lucky, you can observe that transition state and then be able to make conclusions. But again, that's not always the case. And so looking at this state, and so this is interesting. So this is the isomerization of methyl isonitrile. So we have this reactant here. And so we have our methyl group connected to the nitrogen at this point. And then it can do this kind of flip thing. And so it makes this activated complex transition state here, where you have this side unbound methyl group, and then it attaches to the carbon here and makes our product. So then this would be acetonitrile. And so again, activation energy is our difference in energy between the reactants and activated complex, so you remember that, hopefully. And then the frequency is the number of molecules that begin to form the activated complex in a given period. And so as our reaction begins, the CN bond weakens enough for the CN group to rotate. And again, our activated complex is that chemical species with partial bonds. And this can be fairly common too, this kind of side-on bound mechanism. And so looking at our equation, so our exponential factor in our Arrhenius equation is a number between 0 and 1, so it represents the fraction of reactant molecules with sufficient energy so they can make it over the energy barrier. And so the higher the energy barrier, Obviously, the fewer molecules that have sufficient energy to overcome that. We kind of mentioned that before, because again, you have to think about collisions, and they also have to be right in the proper orientation. So even if they collide with the right energy, if they're in the wrong orientation, then you're not going to have productive collisions. And then our extra energy comes from converting the kinetic energy of motion to potential energy in the molecule when molecules collide. And so like we mentioned before, right, if we increase the temperature, that increases our kinetic energy, gives us more productive collisions. And so increasing the temperature will increase the number of molecules with sufficient energy to overcome the barrier, and it should increase the reaction rate as well. And so again, frequency factor is the number of times that reactants approach the activation barrier. So then you could try to quantify this or do experiments to kind of see what this activation barrier is as well. Then our exponential factor is the fraction of the approaches that are successful in surmounting the activation barrier and forming products. So basically, right, how many successful collisions do we have from that? And again, that factor should increase with increasing temperature and decreases with, of course, increasing activation energy. And so this would just be kind of our chart. So we have a bunch of molecules going around. This is just our Gaussian distribution at different temperatures. So we compare, right, T2, so higher temperatures, so more molecules probably able to cross that activation energy versus our T1. So again, our Gaussian distribution, average temperature, and then smaller fraction able to cross that. And so this may be useful, if not for your iodine lab, then some other lab coming up. And so our Arrhenius plots then are just ways to kind of plot this and then give us all the information. So these are, again, experimental measurements of frequency factor. And so the Arrhenius equation can be solved algebraically to give the following form. So you may want to highlight this. So the natural log of K then is equal to the negative activation energy divided by R. So again, R is our constant, times 1 over T, again, T in Kelvin, plus the natural log of A. And so the convenient thing about this form is this gives you the general form of Y equals mx plus B. And so Y is going to be your, of course, natural log of K. X is 1 over T. But then if you graph this, and again, I'm pretty sure you have to do this for one of your labs. But if you graph ln of K versus 1 over T, this would give you a straight line. And then conveniently, right, this would also give you the slope of the line. So if you did negative 8.314 times your slope, that equals your activation energy. So then you'd be able to get EA from this data. And then your y-intercept is just the natural log of A, and A has the same unit of K. Any questions about this equation? Sure. Sure. You finished copying? All right. And then, oops, old notes. Let me erase this. And so I think this was in your lab, and if you don't use this equation, Then your 2-point equation is also extremely helpful. So I think this is definitely the one you use in the iodine lab, at least for sure. And of course, you need 2 temperature points. That's what you did in the lab, right? You did your normal room temperature, and then you got it ideally as cold as possible just to give you the biggest range of temperature. And so then you can solve with this equation as well. And so this is our 2-point form. Again, really important. I would write this down. So our natural log of our rate of K2, so whatever our temperature 2 was, over our K1 is equal to our activation energy over R, so that's 8.314 again, times 1 over T1 minus 1 over T2, and again, temperature in Kelvin. So let people copy that down. Definitely make yourself a formula cheat sheet, yeah. So the first one just depends on like one data point, if you have this. But then usually like our 2-point is more convenient for experiment, because usually we're trying to solve like EA or something. And then experimentally, like we did for the iodine lab, you know, we have T1, T2, we can get K2, K1, and then solve. Sorry, trying to erase all that. All right, so let's look at a sample problem then. So if we look at this reaction, so now we have nitrogen dioxide and carbon monoxide, gives us NO plus CO2. And so it says the rate constant at 701 Kelvin is measured as 2.54, that's molarity per second, and that at 895 Kelvin, that it's 567 per molarity per second. So find the activation energy for the reaction in kilojoules per mole. And then if you need, I can scroll back up to the 2-point. So I'll give everyone a minute or two to do that. see, did we get an answer? Anyone want to go for it? An answer? Natural log. So let's see. So I'll just do K2 as our second one. So 567 over 2.57 is equal to, so we're trying to solve for activation energy, R 8.314. So remember that's joules. So whatever our activation energy is, it's going to be in joules. Times 1 over T1, so make sure I don't screw that up. So 701 minus T2, 1 over 895. And so now we just have to do some algebra. So I'm probably going to solve the parentheses first and then divide. So 1 over 701 minus 1 over 895. Then obviously double check my calculator math. Times 8.314. So do we get that answer? I see some nods there. And then so this would be in joules. I'm going to put it in kilojoules. It actually asks for it in kilojoules, but I also don't like looking at large numbers. So 1, 2, 3. And so that gives us 145 kilojoules N per mole. Oh, but I noticed that, at least on the last quiz, there was like a recurring theme of I need a cheat sheet of equations. So I definitely encourage everyone, like, you know, make your cheat sheet of equations, put it on the back of your periodic table. I can get more periodic tables if people need, or, you know, wherever you need. But I would definitely do a little cheat sheet. There's a lot of formulas, and then, you know, put in parentheses too next to your formula like what the heck it is, because you know in your exam, and you're looking at like little mole, big M, like they all look the same on your exam. So definitely that was a recurring theme. So I highly encourage formula cheat sheets. So you're not digging around the textbook either. Questions about this one? We haven't done this practice problem, have we? I think my notes got screwed up. I just want to make sure we're not repeating. And they all kind of look alike, you know. All right, so I don't think we've done this one. So let's do a little practice. So we have this equation, so 2 equivalents of NO plus oxygen gives us 2 equivalents of nitrogen dioxide. And it says that the rate law has been determined to be K is equal to the concentration of NO squared times oxygen. Then they're giving us these proposed mechanisms. So can we verify that, yes, indeed, this is a mechanism? So I'll give everyone at least a minute or two to get started. So basically, can you rewrite this as this? So let's start going over it together. So kind of the first step, right, was let's at least write our mechanism, our rates, excuse me, of each step. So we can go our first step, we know is equal to, so K1 times, if it's two equivalents of NO, so that's NO squared. But then that's also equal to, right, the backwards reaction rate of K negative 1 now times the N2O4 concentration, so our intermediate there. And then our slow step, so we can write K2 is going to be dependent upon N2O4 times oxygen. And so now we can substitute in for N2O4. So first I'm going to write N2O4 is equal to, so K1 times NO squared over K negative 1. Then we can substitute that into our rate limiting step. And so that gives us, so K2 times K1 over K negative 1. So that just gives us our new K times NO squared times oxygen. So I'll just rewrite that with generic K. And then that indeed does give us back what we were looking for. And then we can also check out that our reaction makes sense, so our intermediates cancel out. And so that does give us two equivalents of NO plus one equivalent of oxygen, gives us 2 of NO2 again, which is again what they gave us. So all that checks out. And so an exam, again, this is mainly what I'd be looking for is, can you do this little proof and prove that yes, these steps do equal our observed rate? Yeah. Oh, equals this? I just went from here, and then I just divided by the K1. So then that gives us the N2O4 concentration.
So on the next one down, how did you get K2 times K1 over minus?
So K2, right, came from there. And then just subbing in for the N2O4, right, that gives us a K1 over K negative 1 times NO squared. And then the oxygen. Does that make sense? Yeah, I mean, like, all we did was substitute it in, so I don't know if it helps if I rewrite it, like, right above.
You just went really fast.
Sorry.
Did it not follow as you were writing?
So yeah, all we did was, so going back to our slow steps, everyone can follow. So we had determined, again, just based off of our reaction, that K2 times our concentration of N2O4 times O2 is what our rate is dependent on. And then all we did was substitute the N2O4 in here. But of course, first we had to solve for N2O4 in terms of our reactants, because that's the only thing we can really observe and report. So then I did that over here fairly quickly. So again, just algebraically dividing gives us that. And then I just sub this expression into our N2O4. And then all these Ks don't really matter, and we just get our new K. All right, we feel better about this?
And so the K times NO2 squared O2 is the rate law for board.
Yeah,
Right?
and that's just what they told us experimentally. Yeah. Oh, you're fine. But yeah, so right, based off of chapter 17, basically, they determined it to be this, which is our reactants, but then we're just breaking it down. How does that work? And so maybe this goes back to your other question too about like the rate law. And because, you look at this reaction and it looks simple, right? Because you're like, oh, well, we have 2 NOs and 1 oxygen. So like, yeah, but we can see, right, there's kind of more to it, which maybe goes back to your original question of how we break it down. Oh, at first it's really 2 NO colliding together. Maybe we can observe this species spectroscopically, or like by mass spec would probably be a good way to see that. So then you could see that large intermediate, because this is going to be like double the mass of everything else. So, I'm not sure how they determine it. I'm just thinking like mass spec would be an easy way. Oh, I see that big species, and then it's going to be consumed by this reaction, and then, we're just breaking it down at this point. This is our proposition, and then, yes, indeed, it does match. And this is just that other problem that we did, but now you can see where the heck I pulled that from. I knew I'd screwed up my notes somehow. So yeah, rerun of the other example. All right, so let's look at catalysts, or at least start catalysts. And I feel like we mentioned catalysts before in this class. Have we? Or am I just... All right, I see some nods at least. And so catalysts are just any substance that affects the rate of reaction without being consumed. And so, of course, this also creates a new mechanism. So, for example, if we're looking at this ozone mechanism, so we have ozone plus oxygen gives us 2 equivalents of O2. And this is a slow reaction. But then if we add a catalyst, so in this case, chlorine radical, so then we have chlorine radical plus oxygen, or ozone, gives us O2 plus this ClO intermediate, and that's fast, which goes on to react with another equivalent of oxygen to give us O2 plus chlorine. This would be some sort of chlorine radical species. And this, based off of this chemistry, so this is probably like some sort of atmospheric chemistry. That's always where you have weird stuff going on. Yeah, not to get into like the whole Ohio thing, but this is, there's a lot of bad things potentially going on in there. But yeah, a lot of like chlorine chemistry can be interesting and reactive, and not necessarily in a good way, but yeah.
Aren't catalysts like not supposed to be included in the mechanism or the reaction? Like, aren't they supposed to just be like helping things along but not actually noted? Like enzymes, for example?
So I guess in this case, like you're forming that species, and so that's what's being emphasized. Like, I think what you're referring to is like in theory, the chlorine should be recoverable for this chlorine radical. But,
Oh, I see. Okay.
but yeah, but there is, at least sometimes with, with chemistry, like there's going to be some sort of species made. So it's still like involved, right? And let me try to pull up some examples of how this works. And so again, factors affecting reaction rates are catalysts. So catalysts are substances that affect the speed of the reaction without being consumed. That being said, it's not always that easy to recover your catalysts. So sometimes they accidentally get consumed. Oops. And so that's what can make, obviously, chemistry and designer drugs expensive, but that's also like going back to catalyst design, is you want something that can be easily recovered so you don't have that issue. And so most catalysts are used to speed up a reaction. And so usually if you at least are talking colloquially, if you say catalyst, you usually are referring to a positive catalyst. And then if you want to say that something is used to slow down a catalyst, you would use the term inhibitor. And so that could also be called a negative catalyst, but again, usually you see inhibitors. Now let's see. see if I like this. This might help us. And so again, just looking at the overall, so transition state, so obviously this blue line here is our uncatalyzed reaction, so high activation energy. And then the whole point here is there's some sort of transition state. And so what's interesting in this catalyzed pathway, the way it's shown here with two little barriers, right, that probably means that there are two elementary steps going on. So that relates back right to these two steps. And so you can also have what's called a homogeneous catalyst, or homogeneous, however you want to pronounce that. And so that means that all species would be in the same phase. So this could be like liquid catalyst. And then heterogeneous catalyst, the best example is like your car. So you have your catalytic converter in there. And so that's a solid piece of metal that the gas flows over. And so that gives you a heterogeneous catalyst where you have species in different phases. And this is usually preferred by industry because that usually means it's easy to separate out the two, and then you can keep using that catalyst, you know, really for a long time. And so let's go back to, so we can talk about, well, how the heck do catalysts work? And again, they provide a whole new mechanism. And so let's look at these Grubbs catalysts. Have I talked about the Grubbs catalyst before? So there's a super famous class of catalysts called the Grubbs catalysts, and they're all carbene complexes, or at least the first generation are carbenes, and they're used for olefin metathesis. And so this is, you know, your general structure of the catalyst. So it has some sort of metal center, these kind of phosphines on it. But then what we care about is, well, how the heck does it work? And so you have basically olefin metathesis is you're like swapping these R groups around. But what happens is your substance first like binds to this metal catalyst, and so it makes this new bond here, this like little 4 bond. And then so it can go on, so it could spit out your reactions of R1, R2. But then if we put it back, so notice R1, R1, so metal binds, so then it gives us, right, our intermediate here. Then notice your electrons kind of flow back around. So that's the important thing about a catalyst, is that it can accept and then release those electrons back and forth, which is much easier said than done when you're in the lab and trying to do this and trying to get it to go. But basically, right, you start with this R1, R1 thing, then the bonds kind of reform because it's attached to that metal catalyst, so then it can make new bonds. So now you swap your R1, R1 for R1, R2, so that makes some new bonds there. And so again, this just repeats now, R2, R2, mixes back, combines on our metal, and we can keep going round and round. But again, it's really cool because it's binding, and so that's the key, right, is it has to interact at some point, in this case with our metal center, so it would bind directly to our metal ruthenium, and then undergo its catalytic conversion. And so many of these catalysts are like second and third row catalysts, so they would try to get first row, obviously for cheaper, but these the second row ones are just better at these multi-electron transfers and tend to make better catalysts. So you can kind of get a glance of what they do or how they look too. And so these are expensive. They would probably be more known as like designer catalysts. This one at least is cheaper, easier to synthesize, but as you go on to like the next generation, so this is more kind of designer. And obviously you don't need like a stoichiometric amount of catalyst. Maybe you just need anywhere from 1 to 5% of your catalyst, but these might be, you know, more difficult to recover than like a heterogeneous catalyst. And so again, in general, a catalyst speeds up our reaction. And so again, it gives a whole different pathway. So you would have to understand that mechanism. It would be a completely different mechanism like we saw with that ozone reaction. And so heterogeneous catalysts tend to hold one reactant molecule in place in the proper orientation. And so this is seen a lot in like some sort of surface catalysis. And you have your, metal surface and, some sort of silicon species or whatever. Could bind whatever you're interested in and then do your catalytic transformation, maybe hydrogenation reaction, whatever you're doing. And then homogeneous catalysts tend to react, again, with one of your reactant molecules to kind of form your stable activated complex with our lower activation energy, kind of like you saw with these grub catalysts. So react and then go on to make your product. So again, homogeneous are all in the same phase. So that was also the case in that chlorine-ozone reaction, so both gases. And then heterogeneous catalysts are in different phases, like I mentioned, your catalytic converter. And so just another illustration. And so the homogeneous, right, again, it'll be reused, but it still has to react, right, one molecule at a time. Then it can go on, make the oxygen, go on to the next ozone, keep continuing. And then your heterogeneous, again, that's going to be like surface-based. And sometimes these can bind, of course, more if you have lots of pockets on your surface. So in theory, right, you can have whatever substrate binds on there and reacting. Yeah, and I mean, you had already mentioned enzymes. So enzymes are good. And somebody else mentioned like doing enzymes for their research paper, so like that would be cool. And I want to see, structures, mechanism if they have it, as much information. Like we want to see, basically, whatever your research is, I want to see the molecule. That's what I care about. And so this would be a hydrogenation reaction. So this probably occurs a lot in industry. And how you make ethane from ethylene. So you have your double bonded here. And so there's your ethene. So it would bind the surface. And it looks like in this case, the hydrogen binds it as well, holding them in close proximity for your hydrogenation reaction, where you're just adding H2 across this double bond there. And so usually these hydrogenation reactions have to be catalyzed, so they tend to be like palladium catalyzed or something. And so many of you like biological catalysts. And so many of these molecules are large and complex. And so most biological reactions require a catalyst to proceed at reasonable rates. So there's all sorts of catalysts. Lactase, what else? Amylase, could go on and on. Maybe name any more for me? Urease. And so protein molecules that catalyze biological reactions are called enzymes. And so, of course, they work pretty similarly to our chemistry ones. Obviously, they're just more complex to be specific to their substrate. And so, of course, they work by binding their substrate on. So you have enzyme plus substrate, gives you your intermediate there. Again, very specific to whatever it's catalyzing. And then we get our reaction, so enzyme plus product. And, of course, recover our enzyme. And so this is just our generic enzyme substrate, kind of lock and key. Again, specific, so we have our active site. And so in this case, right, we have our substrate, binds, and then we get our two products. All right, I think let's go ahead and stop there for now. So we'll pick up on Thursday with kind of a derivation of all this and some fun math. So I don't want to start that right before we end. And then, sorry, losing my voice. I have homework, so come grab homework. And then I'm also going to hand out quizzes as you run out the door. And if you didn't get your exam from me, I should have it in the pile here for you to grab. It worked? Okay, good. I don't know what is up with registration. They yell at us to register when we don't even let you register. And then I will see you for some of you for lab. So I think today we're doing the popping lab that I promised. So it should be fun. Our lab is awesome. Oh, it's are you? I don't mind. I don't know if you're gonna mind later on Thursday.
Well, you know.
Again.
Just like overwhelmed.
Cassandra. And last but not least, Caitlin. No, I got that one wrong, actually.
I was like reading and I was like, I feel like that's what it is, but also, you know.
No, I got that one wrong, actually.
I should. Oh, and I'm gonna stop streaming.
Right, yeah.
I was pleasantly surprised.
Yeah, you did. You're welcome. Anybody see Vaughn? I think so, you saw her last week.
I did, like, was it Wednesday?
That's what he said.
Yeah.
Oh,
There. But then, I didn't see them in class.
For me, it's been writing is my rough draft.
All right, I'm running.
It was like harder.
Yeah, you're running, where are you running to?
Oh, I had,
Yesterday, or
I'm trying to find
technically
people
Sunday,
before
which
they
gave me an
last
extra
week.
day because nothing was in between.
I need a calculus
So,
policy and stuff.
Ah.
I'm gonna try to catch people before they leave. So,
Good luck.
I was very proud of those. I was overthinking them, because I kept going like, what are the sides?
Well,
And
I'm
then I
just
was
trying
like,
to
oh,
do,
it's
I
just.
was gonna do my quiz
It's
today,
just each
but I don't
one.
know if it's I think we asked about this. I don't know if you
And
did.
then
Did
on
you do these with the other two? I was gonna do.
Thursday, for recitation, we have another quiz, I'm assuming. Can I do like, I think I need to do 15 and 16.
Oh, yeah, yeah, that'd be fine.
Yeah. If I need to like move into a different room, I can. It should be. I rewrote those chapters while I was out and about.
Oh, Kennedy, you're still here.
Yes.
Oh, it's just kind of this week.
And then you can always let me know if there are grading errors or anything too on your exam.
My work
No, you
This is
can
old,
keep it.
just-
Okay,
Just, like I said, I would just double check that I added correctly, because, that's gonna be the biggest error, but if I graded incorrectly too, I'm unhappy with. Hey, how's it going? Good.
You guys made me behind the house.
That's not, yeah, that's not bad.
Do you
I
have
don't,
a
more would be
class?
like, how do you even, how do you even do this?
I don't know if you wanna like, come in today and chat, and we could like, go to the lab right now, and figure out what you're missing, but, I don't know, what quizzes you're missing, if they're like.
I know,
ready
I
to
know,
take them.
that was a struggle.
I was just gonna migrate now, unless you
I
want.
only ever get things done when
So
they're
last year was
actually
like
due.
4:30. Yeah, let me just migrate my stuff over there. I am, at least plopping my stuff down.
I'll just go there.
Because I don't want to.
Yeah,